In this video, we'll be going over the memorization approach of distinct subsequences. So previously, our results from the recursive approach has given us a TOE error, so we're going to optimize it using memorization. Let's go over the thought process. The recursive approach is inefficient due to overlapping recursive calls. We can avoid overlapping recursive calls using memorization. Now, what do we need to cache? In each of the recursive call, we are trying to find the number of distinct subsequences at the currents I and j. This means we can cache I and j with subsequences. Let's go over the pseudocode. So we're going to create a 2D matrix, memo to cache previously calculated results. So the rows represent I and the columns represent j, and the values represent distinct subsequences or subsequences. Now we're going to fill memo of -1. This is to prevent the base case or the side case where t is not found in S. Then we're going to implement the top-down memorization approach. And then we're going to pass in our memo into our parameters. And then what's the base case? The base case stays the same. Then if memo I and j is not equal to -1, this means we have already calculated the results for I and j. So we're just going to return memo I and j, return the cache results. Then each of the recursive call, we're still going to create our variable subsequences to keep track of the number of subsequences from our two choices. In the first choice, if we find the number of subsequences, we just move I forward, skipping the current character inside S, and then we're going to increment the number of subsequences by x. And then if the current two characters at I and j are the same, we're going to recursively find the number of subsequences if we move both pointers forward, and then we're going to increment subsequences by y. And then we're going to put subsequences at memo I and j, we cache it, and then we're going to return the results. And then let's go over the time and space complexity. For the time complexity is O of m times n. G is O of m times n plus O of m times n, where mn are the length of the two input strings. The first one is filling memo of -1, and then there are m times n possible states with I and j. And then our space complexity is of m times n plus O of m plus n. So we still get O m times n, and we still get where mn is the length of the two input strings. Now the first one is our cache, so it's our memo, and our second is our recursive call stack memory. Let's go over the code. So this is our code from the recursive approach. Now we're going to create our memo to cache our previously calculated results. And then we're going to fill memo with -1. Now we're going to implement our top-down memorization approach, passing in our memo. Then we update our base case. If memo I j is not equal to -1, this means we have already calculated the results for memo I j, so we just return the cache results. We're going to pass in our memo to our other recursive calls. So the first recursive call is done by just skipping the current character inside S. And then the second one is when the two characters are the same, then we can move both pointers forward. We'll find the number of distinct subsequences by moving both pointers forward and increment it to our subsequences, and then we want to cache subsequences in our current memoij. So we're going to cache it, and we're still going to return our result. Let me know if any questions in the comment section below.